Hello, my name is Evgeny Yakimov, and I'm an application SRE at Bloomberg. And today I'm going to talk to you a little bit about some of the challenges that we run into when we try to apply something cool like distributed tracing to what is effectively a very large asynchronous tracing, so real-time distributed system, and some of the challenges that we ran into in this space. So, what are we going to cover? First of all, I'll talk to you a little bit more about what Bloomberg's about and kind of what are the type of applications that we're dealing with. Then, just to get everyone up to speed, so the basics of distributed tracing, followed up by some of the more complicated aspects of distributed systems, distributed tracing systems. What do they actually look like when you put them together? Moving on from that, I'm going to focus a bit how Bloomberg approached it, so and kind of the differences between some of the open source solutions in this space. Finally, I'm going to introduce you to the actual complicated types of systems that we're dealing with, which kind of introduces the types of challenges we're likely to face, and those challenges. And I'm going to wrap up with a little bit about where we're thinking of going afterwards as well. So, what I hope you'll get out of this is, firstly, if you don't know about tracing, I hope that you'll leave with a somewhat understanding of tracing. But more importantly, kind of where you might run into some troubles and kind of some problems, especially when you're focusing on these kind of streaming style applications, and what you might be able to do about it. So before I get into it, just a quick show of hands. Who would say that they're working on systems that they will say are real-time streaming? So something where you would consider a sub-second latency for your clients. OK, that's a fair amount. So for those of you that put their hands up, how many of you have tried tracing them? OK, well, it's a fair amount. OK, of those of you, how many would you say have been successful in that or have found it easy? 2 people. OK, two and a half. Liz is somewhat varying there. OK. Well, I didn't put my hand up because I did not find it easy. So let me talk to you about why we found it difficult. But before I get into that, just a quick, again, recap of Bloomberg. So most of you hopefully would have seen this. If you haven't, it's downstairs. I'm hoping that by now more of you have seen this than are familiar with the TV channel, because that tends to be the only thing people know about us today. But this is what we're really about. So what is this? This is the Bloomberg terminal. And the best way to describe it is it's kind of a portal to more information than you'd ever know what to do with. So, and ultimately, most of the things that we do as engineers and SREs at Bloomberg is basically bring things to this, as well as some enterprise connectivity, which I'll skip on for now. So, just some quick stats. So, as I mentioned, well, I hope would have been obvious is to power something like the terminal, ultimately, we're more of a technology company than we are a fintech, well, finance company. So although you might know us from finance, ultimately, we do see ourselves as a technology company, and we do kind of look out for technologists to help us solve some of these problems. But as you guessed, we are primarily kind of facing towards finance-based clients, because kind of that's what our data platform is trying to solve. We're going to try to solve their problems mostly. So around 20,000 employees, with about a quarter of them engineering. One of the things that kind of makes Bloomberg quite appealing is we actually have one of the largest private networks. We have presence in pretty much every country to have access to the financial markets and the exchanges, which also adds to some of the challenges I'll talk about later. We do handle quite high loads. So, I mean, just for reference, a tick here is a market data point. So this is when somebody buys something on a stock exchange, for example. And we're really handling fairly high volumes of about 100 billions of these a day. One of the benefits of working for a private company is we don't have kind of quarterly profit margins that we have to deliver against. So we have the ability to invest a lot of our time and effort into kind of providing longer-term solutions to these problems. And one of my favorite things about this company is ultimately philanthropy is at the heart of this organization. Feel free to ask us downstairs for more information on what that means. But this is kind of something that really dominates the culture of the company, everything from volunteering to ultimately having the majority of our profits being put together towards philanthropy initiatives. All right, so let's get into the heart of the topic, distributed tracing. I think the best way to explain this to somebody who might have not worked with these systems is to take an example. So the best example I could find is something you should all be familiar with, which is a search engine. So what's really going on here? I typed in a search query, and a bunch of things happened. Well, the first thing, I obviously had a question I was asking, so my input query is there. But when the page loaded, a bunch of things came up. So there is a main search, maybe there's a new search section. At some point, it realized what I was searching for was a rock band, so it kind of realized that. And then it gave me a bunch of information about that. And then at the same time, I realized, oh, wow, it's a media kind of source of some sort, so there's got to be some songs there. So it gave me a bunch of information about this as well. So ultimately, there's probably quite a complicated system behind all this, and I'm not going to claim that I know what it looks like, but I'm sure there's plenty of people here that do. But I'm going to make a bunch of assumptions of what it could look like, just for the purpose of this demonstration. So let's have a look at the possible architecture view on the left-hand side. And what I'm going to show you on the right is if you trace such a system, what might it look like? You're probably starting off with a load balancer, taking your HTTP request and actually trying to figure out what to do with your query. That quickly probably hits an application, so a search application server. Now, from this point onwards, it's probably a service-oriented architecture, so you're going to be hitting different services, getting different data points. Say you want to classify it as a rock band. Say you kind of want to pull out the information about the rock band. Now they know it's a rock band, it's a media service. Maybe you want to pull in the kind of media-based information, as well as your search that you're doing, and also the news all coming together. Now, as you're looking at what's actually happening in the system, you kind of create this trace-based view where effectively you can kind of see where the time is being spent for each individual part of kind of the work being done. So this is one of the things that tracing gives us in terms of this kind of trace view, but ultimately the biggest value it's given us is the correlation of all the individual items of work done in all these services, and it gives us this ability to track them together. So that's a very quick recap of kind of where you might see it and what it might look like. Let me just introduce a few concepts which are quite common. So first of all, I'm going to be talking about the tracing model based on kind of the span model. This is the more popular one, but there are alternatives. So in this model, what we were looking at initially in the previous slide was a trace. So think of this as an input event into the system that has a bunch of actions, potentially causing a lot of work to be done in different places. Each item or unit of work is normally referred to as a span. You would generally have a span that lives within a single process kind of during the execution of your trace. Now, you may have multiple spans within the same process, but you'd rarely have a span that spans multiple processes. And one extra term I want to introduce is something called a carrier. So one of the things that you probably observed, there's loads of arrows in my previous slides about different services talking to each other. Well, a carrier is basically refers to an implementation of something that propagates tracing data to be able to collect kind of all of these different data points from these different systems and put them all together. So kind of carrier allows you to implement this tracking through your distributed system. Let's go behind the scenes and look at what a tracing system might actually look like. So let's start again with a simple example. I have an application, say a web server, a web application, and maybe that hits some sort of service. I'm not really talking about any specific API at the moment, technology at the moment. So first of all, if you're using tracing, you probably have a tracing SDK. And we're going to take this opportunity to quickly call out OpenTelemetry project, which is hoping to set the standard for what this SDK will be in the future. At the moment, we have OpenTrace and we have OpenSensor. We have a lot of options as well as some in-house options, but a lot of investment is going to creating the one to solve them all. I know there's obviously pitfalls with that approach, but I'm seeing a lot of promise, and I see Liz nodding there, who's been contributing there as well, so I know it's in good hands. All right. So with that out of the way, let's get back to tracing. So the way that your application normally talks to your service, you have some sort of library, both potentially on the client side and also on the service. Now, in this case, those components are probably using the tracing SDK to support tracing. So in this case, the carrier part of the tracing protocol is what these will be implementing for you. Now, to actually collect that data, you generally have a tracer. So this is a component that lives within the application that's actually consuming all the metadata you're producing, all these traces and spans. Normally, you would obviously running your software on a node, whether it be physical, virtual, or even a pod potentially. It's common to have your kind of tracing collection to be done separately. So you can either have an agent running on your host, or potentially a sidecar container running within your node, within your pod. And this will be doing the actual heavy lifting of extracting the traces from your application and propagating it to the right endpoint. Now, then you enter some sort of backend. So at this point, all your tracing data is sent to some engine that you're using that's going to be processing all that data. First thing you want to do is probably going to be store it. So you probably put in some sort of database. But at the same time, you probably want to start analyzing this data, especially for some of the real-time applications such as alerting or kind of monitoring applications. Now, once the data's in there, you probably want to consume it in one way or another, so you probably have some tools. Now, in this case, it's a bit deceiving because both Jaeger and Zip can actually provide a backend component as well. So they would actually be potentially doing this work for you and even having APIs to collect this data. But you can also consider them as a UI that's at the end of this whole thing where you can actually consume the tracing data. And there we go. Well, now that you've got this tracing data being collected, what are you going to do with it? Well, first of all, this is a nice little view that a lot of people have, or views derived from this view, which is kind of like a Gantt chart view. In line with my example earlier, where you can see the search engine, you can see what's going on, what's happening, where it's happening, how long it's taking. Now, going beyond this kind of on-demand interactive workflow, I already mentioned that you can do some analysis on it, the visualization part we just covered. I'll put metrics here in a question mark because this is something I'm seeing happening a lot and something that we're going to be doing ourselves, which is you have this really rich graph-based trace data, but you might only want to extract some data points from that. So maybe you want to extract a data value, such as a latency measurement, or maybe a latency measurement plus using one of the tags or properties to categorize your metrics as well. Now, there's loads of other things you can do with tracing data. I'm not going to claim to know what they are, and I actually don't think anyone here really knows exactly all of them, and I think we're still really discovering that. But hopefully we'll find out what they are in the coming months and years. So how did we go about it at Bloomberg? So I'm going to cover this from the perspective of our telemetry team. So as an application SRE, I haven't really contributed to this, but I have been their primary user, so much so that at the moment we're using 90% of their capacity for just our application. So the telemetry team initially started with the open tracing implementation. Now, in our case, we actually went ahead with our custom implementation of this. It's fairly similar in nature, it's mostly following the same protocol, but there were some constraints that kind of forced us to write our own for the time being. We do have our own agents and applications running to get this data, as well as our own backend. And this is predominantly because we had an existing both log and metrics infrastructure that was in place. So it was easier for us to just simply push our tracing data over this pipeline rather than install a different one from another vendor, as I mentioned before. At that point, now that we have our own backend, we kind of face a challenge. Well, let's say we want to use Zipkin or Jaeger. Well, they normally come with their own backend. So what we did instead is actually just worked with teams like Jaeger and got them to support using us as a backend to actually use their UI to actually see our data. And I'll show you some screenshots coming up as well. How did we go through this experience? Well, as with a lot of teams, we were inspired by what we saw in the Dapper paper, and we tried to give it a go. We tried to kind of localize it and say, we're only going to trace this part of the system or this part of a set of applications. That didn't quite work out very well, because if you're trying to trace only part of the application, unless you really start kind of capturing the beginning of a request or kind of the full journey of the request, you're not really going to get much useful data. You kind of get like a little bit in the middle, and that wasn't really useful for us. So that's not to say that before you get started with tracing, you need to trace everything, but you should really be looking at it from a top-down approach. So look at the most outer level, like trace your load balancers first, and then kind of work your way in to get the depth. But don't try to just pick a tiny bit here and there, because you're not going to see enough of a good picture to figure out what's going on. So as kind of during the process of trying to drive adoption within our teams, we realized if we ask developers to do things, well, they're not going to want to do the work. So we'll try to minimize how much work we actually expect developers to do. And ultimately, that meant that we built it to as much of our existing application frameworks and also into the underlying middlewares that they use. So there's kind of like the carrier and some implementations are done out of the box. They don't have to do anything. So application teams literally just relink their tasks and they get all of this out of the box. So where's our kind of tracing team going next? Well, first of all, we only kind of focused on our RPC level middleware at the moment, so there's definitely loads of other message queues and these type of protocols. I'll talk a little bit about how we did that ourselves, but they want to embed it straight into the frameworks themselves. Obviously, there's more applications and languages and frameworks that people are starting to use at the company, so we want to kind of broaden the coverage to allow them to benefit from tracing by default. There's definitely some enhancements we want to do with our storage, but more importantly, we're going to be spending quite a bit of energy in the short term improving our sampling, the kind of head-based sampling. This is going to be sampling down at the front where you collect the traces. But at the same time, kind of as Liz was hinting earlier, you want to be kind of deferring your sampling decisions until later, until you have more of that context, maybe have tracing data buffered for a 5-minute window where you can make a lot smarter decisions about it. So this is kind of the direction we're looking to go as well. And an interesting thing that I didn't really consider, but when I gave this presentation to our training team, they said one of the things they're going to be doing next is actually teaching tracing as part of the training material to make sure that kind of more developers know what it's about and how to use these concepts and actually incorporate it into onboarding processes. Let's talk a little bit about real-time data streaming applications and kind of the type of apps we try to use tracing in and why that's different. So I'm going to introduce you to a trading system. So what is a trading system? So let's say I have an idea. So let's say I think, you know what, SREcon's got 4 conferences next year, not 3, and I know how much we all love to drink coffee, so I'm going to invest in coffee and try to make a buck out of that. Well, I can make that decision. I can probably call a broker or a bank and say, I want to invest in this on a single stock basis. But what if you're trading thousands or hundreds of different stocks a day? Well, at that point, you need a trading application. And this is what they look like. So what you're seeing on the screen here is a trading application where a trader would have all their orders coming in. They'll have a bunch of data points coming in about those trades or orders that they want to be executing. They're keeping up to speed with the market. They are kind of streaming real-time data about the prices right now so they can jump on those decisions quickly and easily. So some of the characteristics that you can see here is, other than obviously the data set's being painted, what you're seeing around these kind of white cells popping up and down is these are kind of actively streaming protocols where new data is coming in and we get into the screen as soon as we can. But at the same time, some of the data is kind of conflated to take into account that we can't just send all the market data to the client's PC. There's a kind of a messaging pipeline in the middle somewhere there, which is controlling what the client will see and actually kind of processing the data, doing all the number crunching, and ultimately feeding that to an application. Let's talk a little bit about the architecture behind something like this. So I'm going to take the kind of a simplified view. So first of all, you were looking at the application there itself. There's probably some sort of data processing pipeline we have on the client side. Moving up a little bit, so there is a trading system to which you're sending these order messages, and there's probably a database maintaining all those orders. At the same time, those orders are being sent to some sort of data distribution platform where it's sending that data back to you and potentially other people that might be subscribing to similar data sets at that time. Now, a big part of trading is you actually want to send those trades to somebody. And that's where you need this connectivity layer because generally the trading system is connected to the outside world. Now, that means that you're sending messages out and you're also getting messages back in. And these messages are potentially updating your order to say something like, oh, somebody's accepted this order, or maybe you filled part of this order at this price. And to go one step further, again, we had some of those sales which are derived from market data, so we're combining this kind of 100 billion ticks a flow day, 100 billion ticks a day flow, and we're feeding a subset of that back to the user screen. On top of that, we add a bunch of analysis on the data that we do in real time, and we again stream a bunch of numbers back to the user screen derived from both market data and maybe a combination of their order data. But in terms of how far we've gone with tracing so far, well, it's only a subset, but even so, we've kind of experienced quite a lot of difficulty in deploying tracing in just this part of the pipeline with these type of data flows of probably somewhere in the range of tens to hundreds of millions of messages a day at the moment. Let me cover some of the system characteristics that I think make this harder. So first of all, as I mentioned, real-time streaming. So this is not a polling-based protocol. This is an open channel that keeps getting messages kind of being sent, more like an event-based model. A lot of the subscriptions, for performance reasons, are kind of these session-based ones where there's a stateful application that maintains your current state. It's accepting deltas of updates and sending those to you. And it kind of adds additional challenges, such as an initial data load where you first connect. You have to pre-populate these kind of current state. And I'll talk about some of the challenges we had in kind of tracing that part as well. Data distribution, it gets quite interesting because, as I said, you're not going to send all the data to everyone all the time, so you're going to have these interesting patterns where some data points are replicated loads, some data points are conflated, so we have both these fan-in and fan-out kind of interactions in a data flow. And also, given the different kind of network infrastructure and different, I guess, width of the pipe that we have for all these data feeds, we have a lot of flow control mechanisms, whether that means conflating data or kind of queuing or batching. Again, these type of things make tracing a bit non-trivial when you just kind of realize that some messages or some traces get combined into one, and so on. So how did we actually do this? I'm just going to focus on a subset of the system. So first of all, we did stick with the span-based model I introduced earlier. We embedded the tracing into our messaging library, so again, kind of implementing that carrier protocol. On top of that, we actually instantiated the initial spans, which is tracking that work done within each process for the application team, so they didn't have to do that. That was also built into our messaging layer. We did have to add some tracing into the application code itself, especially for middleware that wasn't yet traced. So in this case, for example, pretending to create spans from when the middleware would have done it for us, but because the middleware wasn't traced, they didn't do that for us. There is a big part of tracing which is actually propagating the tracing metadata, context propagation. We've kind of had to do a little bit of that ourselves. We did as much of that we can in the libraries. In some cases, that leaked into application code. And a final point I wanted to mention, because I'll draw upon this later. So most of our relationships are follows from. In the normal tracing model, you generally see more child-off relationships, and this kind of represents the request-response model, where any work done as part of a normal request-response, which has to be done before you respond to the request, is effectively done as a child of that parent request. In our case, that's not the case. You do some work in one component, and you pass it on to the next component to do it. The first component has forgotten about it by that point, and is already working on the next data point. So most of our relationships are ultimately actually follows from relationships. What does it look like? Well, this is an extract of a trace I took a few days ago. I'll call out the fact that I use a test trading system, but ultimately the real one looks similar. Now, let's break this up a little bit. So I don't want to spend too much time talking about this section, because this section mostly looks like what you get in a normal request-response-based trace, which is you have a big span and you have loads of small spans within it. I want to focus more on this section. So this is the more asynchronous part of the application, where this part of the system is no longer waiting for this to respond. It just so happens to be that the synchronous part finished afterwards, but this could have completed afterwards. Let's zoom in a little bit. Let's look at some of the characteristics of the data. So first of all, given that we have an asynchronous cross-process model, we've actually been quite kind of asynchronous in terms of our applications themselves. They don't wait for the data to be sent. They can just say, I've done my part in this part of the process, now hand it over to the next one, because nothing's waiting for that response. So we have a few instances where we have async event handling within the same process. We also see some of these fan-out characteristics where one message was distributed to, say, 6 or 7 hosts there. Also introduces some interesting questions that we are usually interested in, such as, given that this is an asynchronous, you're not waiting for that response kind of pattern within the program, if we want to do something like see what was the latency of this message traveling through this process, then we kind of need to cross over several spans to deduce that. More importantly, we also needed to do things like get the latency across different processes. So in this case, we're taking 2 different spans, and we're trying to see what was latency, what was the end of one, and what was the beginning of the other one. And I'll talk a little bit about this later, but this kind of changes the focus of looking at the spans to instead looking at the kind of the distance between the spans. So if you think of the trace as a graph, effectively we're putting more emphasis on the kind of edges than we are on the nodes, which in this case would be the spans, would be the nodes. And another thing that we're usually quite interested in doing is getting the whole system latency. And in this case, we're suddenly having to, I guess, look at spans across different processes to derive things like what was the journey time of a message as it entered one hop within a system until it exited another. What do we do with all this data now that we've collected it? Well, first of all, we've been using it for issue analysis and triaging. So the type of traces I showed you earlier, we actually use this to identify what the issues are within our system and actually look and debug interactively. This is because we don't do sampling today, which I'll cover a bit more later as well. We do some metrics extraction, so some of the things I was hinting on earlier as well. Ultimately, the most valuable thing I found from the tracing data is we can actually use some of the, for example, subsystem latency metrics that we extract from it to derive our SLOs. If we wanted to observe those numbers in other ways, we might have to kind of embed timestamps and like measure different time points. But using tracing data makes this a lot easier for us. We also perform some more advanced analysis on this data set. So for example, I mean, dependency analysis is quite a common thing you might do with tracing data because, well, you kind of know exactly where a message came from. Some of the kind of less deterministic workflows or questions that we don't even know yet, we found that using something like Jupyter Notebooks, where we can actually just get this tracing data out of a database and ask whatever questions we want, was quite a useful tool for us. So this is definitely something we're doing a lot more of nowadays. And another thing that we've been doing slightly differently to what we see in some of the kind of open tracing and open telemetry protocols is we actually handle our log data separately to our traces. So we have use cases where we combine them at a later time. We found this easier for us because we already have a log propagation infrastructure. So for us, putting those logs into traces didn't make much sense given that we can just stitch them together at the end. Let's talk about some of the challenges, kind of the details of kind of the problems we actually run into. So, I mean, the general theme for all of these challenges is going to be volume. So this is what a span might look like. So this is one span within the trace. And in the previous trace, you probably saw about 10 or 15 of these. And it's quite a heavyweight object. And this is kind of a trimmed down version one as well. So they can easily run into, let's say, a kilobyte worth of size. Now, we're generating about 500 million of these a day, and I know compared to some companies that's not a lot, but if you actually wanted to kind of store that much data for a 30-day retention period, and you went to, say, a cloud vendor and use one of the database solutions to do this, you're getting a pretty hefty bill. It's probably going to run you into $250,000 a year. So I know we have an on-prem kind of infrastructure, so we don't face these bills, but I'm just giving you a comparative analysis elsewhere. Now, even once you do pay for that bill and you use a kind of store that data, what are you going to do with it? It's not very easy to analyze these volumes of data, especially if you don't know what question to ask at the time. And on the topic of why not sample, I'm going to talk at the end about the different strategies we took to sampling and what worked, what didn't work. But ultimately, given that one of our motivations was actually to use this for triaging and debugging, and that the volume of data wasn't really, it's high, but it's not so high that we can't afford to do it, we just decided not to sample from day one. For our application specifically, our telemetry team has been a little bit more vigorous with some of the newer oncomers, but as the first users within the company, we've got a bit of leniency in this space. Let's talk about the nature of the problem. So I mentioned fan out was a problem. So this is usually due to kind of some inefficient distribution. So given the message flows that we have, we can't always know ahead of time, and we can't optimize the traffic to always hit the destination it needs to. So sometimes we send more than we need to. In some cases, it can get pretty expensive where we can actually have discarding of messages of up to the 80% discard rate. This also happens because we run a lot of hot backups in our application. So although the data is kind of needed to keep the backup hot, sometimes that data isn't as relevant for kind of from a telemetry perspective because kind of that's not the thing that's actually powering the client's experience at that time. So once you put this together, you get very noisy traces. So initially we saw a lot of traces like this where we had a bunch of applications say, I've got this, and then do nothing with it. And that wasn't really interesting for us, but it was expensive. So what we did is quite simple. We said, well, we're going to cancel it. We don't care. So if we can work out that you don't care about this, then our tracing API just says, let me tell you that I don't care about you, and it won't bother collecting it, it won't bother propagating it, and at that point, the span just gets undone effectively. So on the reverse direction, this kind of fan in, if you will, we had some situations where we had multiple messages, which are actually bigger messages, which consisted of multiple components. And each one of those message components could take a totally different path through the system. So let me give you an example. So let's say we have a composite message, and this is sent to several different services. But depending on which part of the message you're looking at, they have a different path they might take through the system. And what we really wanted to do is to track each one of the components of that separately. Now, another example where this happened is kind of the initial data loading phase. So when we want to, say, load an initial data set for a client to build up the state, you'd have this very big message which gets chunked into smaller chunks to make sure that that message doesn't, say, interrupt their real-time feed at the same time. What it creates is a scenario where you have different timing dynamics where one chunk of the message is processed immediately, the second one maybe a little bit later, the third one maybe even much further. And we wanted to kind of treat those separately because each one of them kind of is a different data point, if you will, or a different path taken through the system, or different timing exerted through the tracing system. The way we went about this is to actually break up the different parts of the messages to actually create spans. And this is similar to what I would refer to as a dispatching span model applied in a request response space. So normally when you implement tracing, you don't track the time that a process is spent sending a message to, let's say, another service to respond. Generally, you'd only track that span on the service that's responding. But what you can do is say, basically, whenever I make an I/O call out, I'm going to create a span to track the duration of the I/O call on the caller as opposed to the service. And this is effectively what we did even in an asynchronous pipeline. So the outcome was that we changed something from this pattern where, say, we had a multi-part messages published as a whole, and we only saw this type of relationship, to a slightly richer data set where we could actually track the path of each individual part of the message separately through the system, and again, kind of get a better understanding of exactly what happened. Okay, I'll be quick. One of the other problems was a lot of the messages that we send come very quickly, but we want to kind of compress them down and handle them in a smaller subset to the client, because ultimately the client doesn't need to see the updates as quickly as they came to the market. Now, this is to do with high rate of messages, and usually a case where we only care about the last value, and we don't mind if the data gets conflated because the user only cares about the final value. In a lot of cases, this happens by kind of scheduling a interval-based flush that happens periodically. Now, initially, let's say we had this scenario where a message gets sent, and then it gets handled and flushed, but then you get a second message. So the way that we build these applications is generally we defer the flush until, let's say, multiple messages arrive as part of a batch and flush them together. Now, if you try to trace something like this, tracing the first path makes a lot of sense because you just go the publishing of the message resulted in the handling, which resulted in the flushing. But what about the second message? So you know that the second publishing causes a handling of a second message, but which one of them caused a flush? Well, the way we kind of thought about it is, well, they kind of both cause the flush. So at this way, we're effectively thinking of this kind of flush operation as a conflation of multiple traces. Now, this created an interesting dynamic of what I refer to as a distant relationship, where basically you have a span that consolidates multiple traces together. Now, in the data model and the graph-based model, this isn't a problem. But what we found from the tooling perspective is most tools look at a single trace. So you only either see one or the other. It was very difficult for us to get a composite view of both at the same time. And this is something we had to work around. Another thing that we really wanted to do was to kind of get more granularity and get even more spans. But again, given that they're expensive, we wanted to do this in an easy way, kind of in a cheaper way. So what we did is we basically kind of abused tags, if you will, but actually we tried to do something smarter with it. So we introduced a couple of semantic definitions for subsets of tags, where basically we say a tag is a start and an end, or maybe a tag is just a time point. But these kind of had quite kind of defined some semantics that we could understand at a later stage. And when we added it to the code, we basically said, okay, well, I've got my span here that's being tracked, has its own lifetime start and end. But we might say in the middle, well, let's time the beginning and end of just a subset of what the application is doing, or maybe we capture a checkpoint. And at the end, basically, when we get the span, we get this kind of enriched kind of information, more granular data, if you will, but we don't have to pay the cost of the whole span at that time. So it was definitely kind of an easy way to get more granular data without incurring that cost. Sampling. We tried different things. We tried head-based sampling, but this didn't work for us because we wanted to use it for triaging, and therefore we needed as much of the data as we could. We tried this unitary approach. So this is actually quite interesting, where we basically said that traces that pass through a hop, we might just not care about that hop, and presuming that we can tell that somehow that the spans correlate, maybe by looking at a trace ID, maybe that was enough. Now, the only reason we didn't go down this approach further is because we only traced 2 or 3 hops at the moment, and they're all right next to each other, so we haven't yet had too much of an opportunity to put these gaps in place, but we probably will be looking to do this more. But what we really want to do is ultimately invest in a tail-based approach where we can collect all the data and then ultimately make some smarter decisions about how we want to sample that and what we actually want to keep. So let me just talk a little bit about kind of where we want to go next with this. I already kind of hinted that we only trace a small subset of the system, but there's still a lot more to go. There's still a lot more we could be tracing, specifically the client side. We've been talking mostly the backend infrastructure today, but as I showed earlier, there is a big data processing part of our application on the client side, And it'll be interesting to understand when are those messages actually hitting their system and what kind of latencies are. And ideally, we want to be collecting things like SLOs based on when did the user click a button until that data point showed up back on their screen. And to get this level of granularity, given that we have a lot of these same problems about data flow, conflation, flow control on the client side, we're going to have to apply a lot of these same mechanisms on the client side as well. I refer to this as near real-time data processing, but I think Liz had a slightly different term for it, kind of buffering and doing analysis on this. Ultimately, a lot of the questions that we want to ask can be answered in a near real-time basis as long as we can do an analysis of the last 2 to 5 minutes on the tracing data. So we're basically trying to make our systems kind of maintain this cache and then ask questions of that data in real time and produce kind of derivative statistics on it. Maybe that's extracting metrics. Maybe that's making sampling decisions to decide whether we want to keep this data for longer or not, or maybe even to trigger alerting at some point, which is exactly what you said, and alerting. So just to wrap up, I want to say if you've been interested in this type of problems, then we're hiring. We have a booth downstairs, so feel free to talk to us later. And thank you very much for listening, everyone. And I was hoping to have time for questions, but I guess I don't. You have 5 minutes for questions. Oh, I have 5 minutes for questions. Awesome. Cool.
So questions? Are you sure? Oh, there's. Oh, okay. You're not sure.
Thank you very much. We seem to have a lot in common in the journey to tracing. I am particularly interested in, I think you called it the conflation. Just to see if we are on the same page, this is when these asynchronous messaging exchanging systems do batching, for example, where a publisher will batch and tag all of those matches with a certain parent ID, but then the consumers will eventually consume messages having different parents. Is this the case?
Can you just repeat the final part of the sentence? Sorry.
Your consumers, for those asynchronous messages, will eventually find messages containing tracing in the span context of that different parent IDs.
So in this case, actually, we make a transformation of the data. So it's not like it's a batching, it's more of a compression. So at this point, the raw events may lose their initial meaning because we decide to combine 2 events into a single composite event. Say they're updating the same column or the same part of the data, and ultimately we only care about the latest update. So in this case, because we've compressed the data rather than kept it just putting 2 messages together but then processing separately, it didn't make sense for us to then track each individual component of that message separately. So at that point, we were able just to say, well, actually, as part of this conflation, we only now have the one span that makes sense to track because the consumers will only process that as a single unit going down, kind of downstream. So in our case, it's less of a batching and more of a conflation. So as such, because we can then just say that that conflation event has one span, that's the only thing that the child spans would relate to, or the follows on spans would relate to. But the conflation span itself does reflect the parents from all the messages that were kind of sent to it. So that's how you maintain that relationship.
Just to be clear, this is what you found that the open tracing data model will not allow you to do.
So I guess we follow the data model, but maybe we're not that constrained. In our cases, we kind of made a copy-paste of that data model. So our references do allow us to do a distant relationship, which is what I referred to as earlier. The problem was the tooling. The tooling didn't allow you to consume and visualize it that way because they only looked at single trace basis. Yeah. But in our database, kind of we do maintain those relationships, and you can traverse them if you want to.
Hello, thank you for presentation. I'm David Brunatan from Yandex. I have a question about around tracing. We have tens of teams, 100 or maybe 1,000 of developers, and a lot of services that appear new. And for us, it's very hard to find new service that don't do tracing. And do you something with that, maybe some discovering or something like that to find the service that not covered by tracing? Thank you.
Okay, so this is a bit of a difficult question there is not an easy way to discover things that aren't being traced. The best way I can describe this problem, let's say you build tracing in by default. So this is what we did earlier. We built it into our application infrastructure. So if you use our application frameworks to go and create your app, you get tracing by default. But then you do something whilst handling that trace where maybe you don't propagate the span information within your process. So let's say you have your own threading model that doesn't propagate tracing data. So even though you catch the application and you know that maybe a trace came into it, you lose the joining path downstream. So I mean, obviously the first part of that message is build it into your application frameworks and you get a lot of stuff for free, but that's not going to give you complete coverage. And you're always going to get those situations where traces are created by kind of at weird points. Now, presuming your systems support tracing even if there's no parent. So you can basically say, I will create a span regardless of whether I can find my parent or not. What that will allow you to see is to see traces starting at weird places. And I'm out of time. So if you see traces which start in weird places, then that's usually the first place to focus on. But before you get that far, you need to make sure that tracing is built in by default into your application frameworks.
And we're done. Okay, thank you very much.
All right, thank you for listening.